Welcome back to QHSE Talks.
Glad to be here.
So imagine walking into a pristine, brightly lit room. It's totally silent.
Right.
There are no exposed gears, no open trenches, no chemical fumes stinging your eyes, and no deafening noise from heavy machinery.
Sounds completely harmless.
Exactly. Your brain relies on, millions of years of evolutionary survival instincts, and it tells you that you're perfectly safe. But in reality, the environment is actively and violently destroying your cellular DNA.
Yeah, that's the scary part.
You can't see it, you can't hear it, you can't smell it, and by the time you actually feel it, the damage is already irreversible.
It really is the paradox of industrial hygiene when dealing with radiation. We're wired to react to tangible threats, right? Like a falling brick or a spinning blade.
Right, stuff we can see.
Exactly. So when the threat is entirely invisible to our biology, we have to rely entirely on our intellect. We literally have to substitute mathematics, physics, and instrumentation for our five senses.
And that is exactly what we're doing today. If you're an industrial hygienist managing a facility, or maybe you're a safety professional rigorously preparing for the ASP version 11 exam.
Good luck to you if you are.
Yeah, especially Domain 1, Topic 15. You already know that calculating radiation exposure is a massive hurdle.
Oh, absolutely. It's tough.
We are talking about shielding, half-life, and dosage calculations, and we are going to master this today. But we really need to establish the stakes right away.
Definitely.
We aren't just reviewing these concepts so you can, circle the correct letter on a multiple-choice test.
Not at all. I mean, the mathematics of radiation are the literal blueprints for human survival in hazardous environments.
That's a great way to put it.
When a safety professional sits down to calculate, say, a half-value layer or run an inverse square law equation, they are designing an invisible guardrail. Mastering these calculations is how you determine the exact thickness of a concrete wall needed to protect a control room, or the precise number of minutes a worker can perform a critical repair before their internal biology begins to fail.
Okay, let's unpack this. We have to understand the fundamental mechanics of the threat before we can start throwing numbers at it.
Makes sense.
Let's look at the actual physics of ionizing radiation. What exactly makes this type of energy so destructive compared to, say, the light bulb above my head or the radio waves carrying a broadcast?
Well, it all comes down to a very specific threshold of raw energy. When we talk about ionizing radiation, we're referring to electromagnetic waves or subatomic particles that carry enough kinetic force to literally strip an electron away from the orbit of an atom.
It's basically an act of microscopic violence.
It is precisely that. I mean, atoms are normally electrically neutral, right? The positive protons in the nucleus are balanced by the negative electrons orbiting them.
Okay, sure.
But when an incoming particle of radiation slams into that atom, it can knock an electron completely out of its orbital shell. This just severs the bond entirely.
Wow.
You're left with what we call an ion pair. So the freed electron goes rocketing off as a negative ion, and the rest of the atom, which is now missing a negative charge, is left behind as a positively charged ion.
And here is where I see people get tripped up on the exam, and frankly in the field too. The distinction between ionization and excitation. Because the energy doesn't always knock the electron completely out, right?
Correct. And that is a crucial distinction. Excitation happens when the incoming radiation transfers some energy to an orbital electron, but just not quite enough to sever the bond entirely.
So it just shakes it up a bit.
Basically,
Yeah.
The electron absorbs the energy and gets pushed into a higher, more distant orbit from the nucleus. It becomes excited.
Gotcha.
But eventually it's going to drop back down to its stable state. And when it does, it usually releases that extra energy as a harmless photon of light or maybe a little bit of heat. The atom itself stays structurally intact.
But with ionization, the electron is permanently evicted.
Yes, permanently gone.
And why does that matter so much to a safety professional? I mean, human DNA is just a highly complex, fragile arrangement of atoms holding onto each other by sharing those exact electrons.
Precisely.
If you start ripping electrons out of the system, the chemical bonds holding the DNA double helix together literally snap. The genetic code gets shredded.
Exactly. When you cause widespread ionization in living tissue, you aren't just heating the cells up. You are fundamentally altering their chemical structure.
Which leads to mutation.
Mutation, cell death, and radiation sickness. It's devastating.
So we need to know what kinds of subatomic wrecking balls are capable of doing this. Let's break down the cast of characters. What are the primary types of radioactive decay that a safety professional needs to calculate protections against?
Well, it helps to understand why decay happens in the first place. A radioactive atom is simply an atom with an unstable nucleus.
Meaning it has too much energy.
Yeah, too much energy, or maybe the wrong ratio of protons to neutrons. To find stability, it just has to throw something out. And the first and heaviest thing it can throw out is an alpha particle.
Okay, alpha decay.
Right, alpha decay is when the nucleus ejects a massive cluster consisting of 2 protons and 2 neutrons.
So an alpha particle is basically a helium nucleus, just without the electrons.
Yes, exactly. And because it literally loses 2 protons and 2 neutrons, the original atom fundamentally changes.
It's not the same element anymore.
Not at all. Its atomic mass drops by 4, and its atomic number, which is what dictates what element it actually is, drops by 2.
Do you have an example?
Sure. For instance, radium-226, which is an intensely radioactive metal, undergoes alpha decay and physically transforms into radon-222, a radioactive gas. It's literal alchemy.
That's wild. Okay, then we have beta decay. If alpha is ejecting a massive cluster, what is beta doing?
Beta decay is much stranger, honestly. This is when the unstable nucleus ejects a high-speed, high-energy electron.
But wait, there are no electrons in the nucleus, right? Only protons and neutrons.
Exactly. That's the weird part. What actually happens is that a neutron inside the nucleus spontaneously converts into a proton. And in the process, it spits out an electron to conserve the overall charge.
Okay, I follow.
That ejected electron is the beta particle.
So the mass of the atom barely changes because an electron's mass is basically 0 compared to a proton. But the atomic number actually goes up by 1 because we gained a proton.
Precisely. Strontium-90 undergoes beta decay and becomes yttrium-90. The mass stays at 90, but it moves 1 space up the periodic table.
Okay, so alpha and beta are physical particles with actual mass. But then we have gamma rays and X-rays.
Right, and gamma and X-rays are not particles in the traditional sense. They have 0 mass and 0 electrical charge. They are pure, highly penetrating electromagnetic energy, just photons.
Where do they come from?
Gamma rays originate from the unstable nucleus itself as it sheds excess energy. X-rays, on the other hand, originate from the electron cloud outside the nucleus. But for health physics purposes, they are identical hazards, just highly penetrating waves of energy.
And just to be completely comprehensive here, there are 2 other mechanisms we should mention from the sources, right? Positron emission and electron capture.
Yeah, we should cover those. Positron emission is the exact mirror image of beta decay.
So instead of a neutron turning into a proton
converts into a neutron, and to conserve charge, it ejects a positively charged electron, a positron.
And electron capture.
Electron capture is when an unstable nucleus actually pulls in one of its own inner orbital electrons. That electron merges with a proton to form a neutron. In both of these cases, the atomic number drops by 1.
I always try to visualize these hazards, to understand how they interact with the physical world.
It definitely helps.
An alpha particle is massive. It has a +2 charge. To me, it behaves like a microscopic bowling ball rolling through a field of fragile glass pins.
I like that analogy.
It's huge, it hits hard, but because it's so massive and highly charged, it interacts with everything immediately. It smashes into the first few atoms it encounters, dumps all its energy, and stops abruptly.
Exactly.
A beta particle is more like a high-speed bullet, much smaller, much faster, with a -1 charge, which allows it to penetrate deeper before it hits something.
Right.
And gamma rays are like high-powered, invisible laser beams that just go straight through most matter without interacting at all until they hit something very dense.
That geometric visualization is highly accurate for predicting penetration depth, for sure.
But here's the critical analytical pushback. I mean, if the alpha particle is this massive, slow-moving bowling ball that stops immediately, and we know that a single sheet of standard paper, or even just the microscopic layer of dead skin cells on the outside of the human body, can completely stop an alpha particle in its tracks.
Yes, that's true.
Then why is it considered such a catastrophic hazard in industrial hygiene? If my dead skin blocks it, why do we even care?
Well, because of the profound difference between an external exposure and an internal exposure.
Ah, okay.
Outside the body, you're totally correct. An alpha source sitting on a table is relatively harmless to your internal organs because your dead skin acts as an impenetrable shield. But what happens if the environment is contaminated with alpha-emitting dust?
Oh boy.
What if a worker inhales radon daughters in a poorly ventilated mine or accidentally ingests a fleck of polonium?
Then the source is physically inside the body, past the barrier of the skin.
Exactly. Once an alpha emitter is lodged in the mucosal lining of your lungs or sitting in your digestive tract, there is no dead skin to protect you.
It's just bare tissue.
That massive +2 charged bowling ball is now rolling directly through soft, living, highly sensitive cellular tissue. And because it starts so quickly, it dumps 100% of its massive destructive energy into a microscopic radius.
That's terrifying.
It doesn't just damage a cell, it completely obliterates the surrounding tissue. That localized devastation is why internal alpha exposure is one of the most lethal hazards we face.
That makes the stakes incredibly clear. It really is about where the interaction happens. Now, to anchor this physics discussion, there are a couple of fundamental constants we have to respect, right?
The electromagnetic relationships, yeah.
The relationship between energy, wavelength, and frequency. We're dealing with the speed of light equation, where c equals wavelength times frequency, and Planck's equation, where energy equals Planck's constant times frequency. This basically tells us that higher frequency means higher energy.
And that ties directly back to our threshold of ionization. The baseline requirement to eject an electron and start this whole destructive chain reaction is approximately 10 electron volts, or 10 eV.
So if the incoming photon or particle has less than 10 eV, it might excite the atom, it might heat up the tissue like a microwave does.
Right, but it won't ionize it.
It won't shred the DNA. Knowing that 10 eV threshold is what allows industrial hygienists to draw a hard line between non-ionizing hazards like radiofrequency or infrared and true ionizing hazards.
Absolutely. The safety protocols for those two realms are completely different universes.
Which brings us to the most notoriously difficult aspect of this field. The units of measurement.
Oh, yes.
The alphabet soup. I hear this complaint constantly from professionals in the field and from people studying for the ASP exam. The units used in radiation safety feel almost deliberately designed to confuse people.
It can certainly feel that way.
It's a dizzying array of Curies, Becquerels, Röntgens, Rads, Greys, Rems, and Sieverts. Why can't we just have one unit to measure radiation?
Because radiation isn't a static object we can just, weigh on a scale. It's a dynamic process.
Okay, what do you mean by that?
To properly assess the risk, we have to measure the hazard at 4 distinctly different stages of its journey. At the source, in the air, in the physical tissue, and finally in the biological outcome. If we decode them sequentially, the confusion really disappears.
All right, let's track the life of a radioactive emission then. Stage 1, the source itself.
Stage 1 is activity. This simply measures what the radioactive material is doing. How many atoms are disintegrating or decaying every single second.
So it's not about the type of radiation.
No, we aren't looking at what kind of radiation it is or where it's going, just the raw rate of decay. The traditional unit here is the Curie, named after Marie Curie. And it's really vital to understand that 1 Curie is a staggering amount of radioactivity.
What's the exact definition?
Originally, it was based on the activity of 1 gram of radium-226. Mathematically, 1 Curie equals 3.7 times 10 to the 10th power disintegrations per second.
Wow.
Yeah. That is 37 billion atoms exploding every single second. Because that number is so unwieldy, the international community adopted the SI unit, the becquerel, which is beautifully simple.
What is it?
1 becquerel equals exactly 1 disintegration per second.
So activity is just the raw output.
Yeah.
If the source is a light bulb, the Curies or becquerels tell me the wattage. It tells me how bright the bulb is burning.
Exactly.
And along with that, we measure the energy of the emissions in electron volts EV or megaelectron volts MeV, which tells us the penetrating power. But none of that tells me what happens when the light actually hits something.
Right. So we move to stage 2, the journey through the environment. The radiation leaves the source and travels through the air toward a worker. We measure this as exposure, and the unit is the Röntgen.
And the physical definition of the Röntgen is very specific, isn't it?
It is, and it's a fundamental concept for environmental monitoring. The Röntgen is defined as the amount of X-ray or gamma radiation required to produce 1 electrostatic unit of charge in exactly 1 cubic centimeter of dry air at standard temperature and pressure.
Wait, let's break that down. It's literally measuring the ionization of the empty air.
Yes.
It's measuring how many electrons are being ripped off the oxygen and nitrogen molecules in the air before the radiation ever even touches a human being.
Precisely. You're measuring the hazard potential of the environment itself. But a Röntgen in the air doesn't equal damage to a human. So when that radiation finally strikes a worker, we enter stage 3, absorbed dose.
Now we need to know how much of that energy actually transferred into the physical mass of the worker.
And that unit is the rad, which literally stands for radiation absorbed dose. We define 1 rad as the absorption of 100 ergs of energy per gram of physical tissue.
And the SI unit.
Or the modern SI equivalent is the gray, where 1 gray equals exactly 100 rads.
Okay, so the rad tells me the raw physical amount of kinetic energy my tissue absorbed. But I have a major analytical problem with stopping here.
Go for it.
If we go back to our bowling ball versus laser beam analogy, surely a specific amount of energy delivered by massive alpha particles causes a vastly different type of cellular destruction than the exact same amount of energy delivered by massless gamma rays.
Right. That insight is exactly why the rad is insufficient for safety planning and why we must move to stage 4, biological dose equivalent.
Okay, stage 4.
We have to account for the biological reality that not all radiation is created equal, even if the absorbed energy is identical. The unit we use for this final, ultimate measure of human harm is the Rembrandtchen equivalent man.
And the SI unit for that.
The SI unit is the sievert, where 1 sievert equals 100 rems.
How do we mathematically translate physical energy, the rads, into biological damage, the rems?
We apply a multiplier called the quality factor, or QF. The equation is incredibly straightforward. Rems equal rads multiplied by the quality factor.
And these quality factors aren't arbitrary. They're strictly defined based on the particle.
Right.
For X-rays, gamma rays, and beta particles, the quality factor is 1. So for those, 1 rad of energy equals 1 rem of damage. It's a 1-to-1 ratio.
But if the particle gets denser and heavier, the multiplier scales up aggressively. For thermal, slow-moving neutrons, the QF is 3. For fast, high-speed neutrons, it jumps to 10. And for alpha particles, the quality factor is 20.
A multiplier of 20. That means an alpha particle inflicts 20 times the biological destruction of a gamma ray, even if the physical energy absorbed is mathematically identical.
Yes.
Why is the disparity so massive?
Because of a concept called linear energy transfer, or LET. This describes how a particle distributes its energy along its path through tissue. Gamma rays have a very low LET. They are like a speeding sports car on a highway. They travel a long distance and only occasionally bump into things, spreading their energy out over a large volume of tissue.
Yeah.
The damage is very diffuse.
But the alpha particle?
The alpha particle is a bulldozer. It has an incredibly high LET. Because of its massive size and +2 charge, it cannot travel far. It dumps 100% of its energy into an incredibly short microscopic path.
Just massive local damage.
Exactly. Instead of slightly damaging 100 cells over a long track, it absolutely obliterates 1 single cell and its neighbors, completely shattering the DNA beyond any biological repair mechanism. That localized catastrophic cellular devastation is why the multiplier is 20.
Understanding LET completely unlocks the why behind the units. So when we look at safety regulations and legal limits, everything is written in rems or sieverts because that is the true metric of human harm. Let's talk about those limits and the biological realities of hitting them.
Well, the acute effects of radiation are highly predictable. If a worker receives an acute whole-body dose between 0 and 25 rems, there are generally no observable immediate clinical effects.
What happens when it gets higher?
As you cross into the 25 to 50 rem range, you begin to see minor temporary drops in white blood cell counts.
And as it climbs, the symptoms become catastrophic.
Very much so. At 400 rems, you have reached the LD50-30. That means it is a lethal dose for 50% of the exposed population within 30 days without significant medical intervention. At 600 rems, it approaches LD100, near total mortality.
And because radiation targets cells during the division process, the most sensitive tissues in the human body are the ones that divide the fastest, right?
Precisely.
The lymphocytes, your white blood cells, are highly radiosensitive. The bone marrow, the lining of the gastrointestinal tract, the reproductive organs, these are the critical targets that fail first.
To ensure no worker ever approaches those acute levels or accumulates dangerous chronic levels, OSHA and the Nuclear Regulatory Commission enforce strict legal boundaries. For an adult radiation worker, the annual effective dose equivalent limit is set at 5 rems per year.
Or 0.05 sieverts.
Correct.
Now, historically, there was an older formula for lifetime limits from the text, right? The 5 times n-18 rule, where n is the worker's age.
Yes, that's a classic one.
So if a worker is 30 years old, minus 18 is 12, times 5 equals a maximum lifetime accumulation of 60 rems. It's a useful historical context, though modern compliance focuses intensely on the strict annual limit.
But focusing purely on the legal limit is a trap.
Yeah.
If your worker ends the year at 4.9 rems, technically you are legally compliant,
Yeah.
But are you practicing good industrial hygiene?
Not even close.
Yeah.
And that introduces the bedrock philosophy of the entire field, ALAR archival, as low as reasonably achievable.
Right.
Compliance does not mean treating 5 rems as a target or an allowance to be spent. ALARA demands that you constantly ask, could we have engineered this process to expose the worker to only 1 rem? Could we have shielded them better and achieved 0.1 rems?
Exactly.
You must actively minimize exposure below the limits using every resource and control measure available.
That philosophy requires action, and action requires calculation. Which brings us to the actual mechanics of controlling exposure, starting with the inevitability of radioactive decay.
Let's get into the mathematics of time. If a facility has a radioactive spill, or if we are engineering a long-term storage solution for hazardous waste, how do we confidently predict how long that hazard will threaten human life?
We rely on the universal constant of the half-life, usually written as T1/2. The concept is elegant, really. The half-life is the exact amount of time required for 50% of the unstable radioactive atoms in a given sample to decay into a more stable state.
It's important to clarify that this isn't an average or an estimate. It is an immutable law of physics for that specific isotope.
Absolutely immutable.
Yeah. You cannot speed up a half-life by tossing the material in an incinerator, and you cannot slow it down by dropping it in liquid nitrogen. Chemical reactions, pressure, temperature, none of it alters the nuclear decay rate.
And the sheer spectrum of these half-lives is staggering. You have isotopes like radon-219, which has a half-life of 3.96 seconds. It essentially blinks out of existence.
But then you have the long words.
Right. Then you look at carbon-14, which takes 5,730 years for half of it to decay. Or plutonium-239, a primary component of nuclear weapons and reactor waste, which has a half-life of 24,110 years.
Which perfectly explains why deep geological repositories for nuclear waste require engineering blueprints that must survive longer than recorded human civilization. We are quite literally outweighting the physics of the universe.
True. But in the day-to-day operations of an industrial hygienist, you don't just conceptualize half-life, you have to calculate precise decay curves. You have to use the master decay equation.
Let's discuss the architecture of this equation. Without turning this into a dry math lecture, the formula is built around an exponential relationship. Nt equals N0 multiplied by e to the power of negative gamma times time. Let's define these variables conceptually.
Think of it as a ledger of atoms. N0 is your starting balance, the initial amount of radioactivity you possess right now.
Okay.
Nt is your future balance, how much radioactivity will remain after a specific amount of time has elapsed.
And the E?
The E is Euler's number, the base of the natural logarithm, which mathematically governs continuous exponential growth or decay in nature.
The trickiest part of the exponent is gamma, the disintegration constant. When you face these calculations in real life or on an exam, they almost never hand you the gamma constant, do they?
No, they almost always give you the half-life.
How do we translate half-life into the disintegration constant?
It's a fixed proportional relationship. Gamma is always equal to the natural logarithm of 2, which is roughly 0.693 divided by the half-life of the specific isotope.
Okay, so 0.693 over T1/2.
Right. By dividing 0.693 by the half-life, you convert a time-based concept into a continuous rate of decay that the exponential formula can actually use.
Let's talk through the real-world application of this. Let's look at a scenario with strontium-90, a very common, highly dangerous byproduct of nuclear fission.
Good example.
Let's say a contaminated site has an initial activity of 50 gigabecquerels per gram. We know the half-life of strontium-90 is 29.12 years. As a safety professional, you need to predict the exact activity level 14 years from now to plan future remediation efforts.
The logic flows sequentially here. First, you need your decay rate. You take that constant, 0.693, and divide it by the half-life of 29.12 years. This gives you a disintegration constant of roughly 0.0238 per year.
So that's the steady annual drumbeat of decay.
Exactly. Then you apply that rate over the time span in question, which is 14 years. So you multiply the annual rate by 14, making it a negative exponent because the material is decaying, not growing. When you run that continuous exponential decay function over the 14-year span, you generate a decay factor. In this specific case, the math reveals a factor of approximately 0.716.
Let's pause and analyze that number, because this is where human intuition often fails. 0.716 means that 71.6% of the original radioactive material is still entirely active and hazardous.
That's right.
14 years have passed, a massive amount of time in terms of human operations, and almost 3/4 of the threat is still sitting there.
which logically aligns perfectly with the half-life. I mean, if it takes 29 years to reach 50%, then at 14 years, roughly half of a half-life, you would expect the drop to be relatively shallow. You certainly wouldn't expect it to be halfway gone.
It's not a straight line.
No, the decay curve is not a straight steep line. It's a long sloping asymptote. It decelerates.
And when you multiply that 71.6% remaining factor against the original 50 gigabecquerels, you find that the site will still be emitting over 3,600 gigabecquerels per gram a decade and a half from now.
It fundamentally alters how you approach the site. You can't just wait it out. You have to actively shield and remediate it.
But the math works in both directions. We just wound the clock forward. Safety professionals often have to wind the clock backward, especially during incident investigations or discovering legacy materials.
That's true. Retrospective math is very common.
Let's talk about that scenario. Imagine a facility audit uncovers a sealed source of cobalt-60 in a forgotten storage locker. You test it today, and the meter reads exactly 2 curies. But the purchasing records indicate this source was acquired exactly 10 years ago.
Okay.
Cobalt-60 has a half-life of 5.24 years. You need to know how dangerous this source was when it was originally in active use a decade ago.
You use the exact same master equation, but you algebraically invert the goal. Instead of predicting the future, you're reconstructing the past.
How do you flip it?
You know, the current NT is 2 curies. You simply change the sign of the exponent from negative to positive. You are mathematically forcing the decay curve to run in reverse, growing instead of shrinking.
Right, so you find your gamma rate by dividing 0.693 by the 5.24-year half-life. You multiply that by the 10 years that have passed. And when you calculate the exponential growth factor backwards, it comes out to a multiplier of about 3.75.
Meaning the source was nearly 4 times as powerful when it was bought. You multiply the current 2 curies by that 3.75 factor, and you discover the original source was blasting out 7.5 curies.
Why does an industrial hygienist care what the activity was 10 years ago if it's weaker now?
Retrospective dosimetry.
Exactly. If an older worker suddenly develops a specific leukemia and you discover they routinely handled that cobalt-60 source a decade ago, you cannot use today's 2 curie reading to calculate their historical exposure.
No, you absolutely cannot.
You must use the 7.5 curie mathematical reconstruction to determine if they suffered a severe overexposure event in the past. The math is the only historical record that never lies.
It really provides absolute clarity. Now, managing time on a timeline of decades is one thing, but how do we manage the immediate acute exposure of a worker standing in a radiation field right now?
We have to move from the physics we can't control to what we can.
Right. We transition from the uncontrollable physics of half-life to the highly controllable engineering levers of the safety triad: time, distance, and shielding.
Let's start with the most basic administrative control: time.
The relationship between time and dose is perfectly linear. Dose equals the dose rate multiplied by time. If a pump in a contaminated zone is emitting a field of 500 millirems per hour and a worker spends 2 hours repairing it, they receive 1,000 millirems, or 1 rem.
It's simple arithmetic, but it forms the backbone of a complex logistical ballet called worker rotation.
Very complex.
If a task requires 10 hours of labor in that 500 millirem per hour field, the total cumulative dose for the job is 5,000 millirems, or 5 rems. That is an absolute maximum legal limit for an entire year. One worker cannot complete that job.
If they do, they are legally barred from performing any radiation work for the next 12 months.
So the industrial hygienist uses the math to slice the task up. You calculate that a worker can safely spend exactly 45 minutes in the zone to receive a planned ALARA compliant dose.
You set up a strict administrative stopwatch. Worker A enters, works for 45 minutes, tags out, worker B tags in.
It requires meticulous oversight, but it effectively dilutes the total task dose across a larger population.
But there are situations where you cannot simply rotate an army of workers through a hot zone. You need to reduce the dose rate itself. And that brings us to the second and arguably most powerful lever in radiation safety: distance.
Ah, yes, the inverse square law.
This involves one of the most elegant and critical concepts in physics. The inverse square law states that the intensity of radiation from a point source is inversely proportional to the square of the distance from that source.
Let's get the equation out there.
The equation is straightforward. Intensity 1 over intensity 2 equals distance 2 squared over distance 1 squared.
I don't want to just recite the formula, though. Let's explore the physical geometry of why this happens. Why does the radiation drop off so incredibly fast the further you step away?
Well, you have to abandon the idea of radiation behaving like a linear laser beam. Imagine a tiny radioactive point source suspended in the center of an empty room. When it emits radiation, it doesn't shoot in one direction. It emits in every direction simultaneously.
So it's spreading out in 3D.
Yes. It creates an expanding, perfectly spherical wave of energy.
Like inflating a balloon.
Exactly like inflating a balloon. Now, the total amount of energy trapped on the surface of that balloon never changes. The source emitted a fixed number of photons. But as the balloon expands, the surface area grows massively.
Because of the math of a sphere.
Right. The formula for the surface area of a sphere is 4 times pi times the radius squared. Because the distance is squared, the surface area increases exponentially.
So you have the exact same amount of total energy, but it is being stretched thinner and thinner across a vastly larger surface area.
Yes. If you double your distance from the source, the surface area of that energy sphere doesn't double, it quadruples. Therefore, the amount of energy hitting any specific 1 square inch target, like a worker's body, drops to 1/4 of its original intensity.
And if you triple it,
If you triple the distance, the area increases by a factor of 9, so the intensity drops to 1/9.
that geometric expansion is the safety professional's best friend. Let's analyze the practical impact of this. Suppose a technician is standing 1 foot away from a radioactive source, and their survey meter reads an intensity of 148 millirems per hour.
Okay, 148 at 1 foot.
The safety manager instructs them to take 2 steps back, moving their working distance to 3 feet. How radically does the hazard diminish?
We use the proportional relationship of the inverse square law. Since the distance increased from 1 to 3 a factor of 3, we know the intensity must decrease by the square of that factor, which is 9.
So you just divide.
You simply divide the original 148 millirems per hour by 9.
And the result is roughly 16.4 millirems per hour. By merely stepping backward 24 inches, the worker has slashed their radiation exposure to almost 10% of the original danger. Distance is a phenomenally powerful mitigative tool.
It really is. But the blade cuts both ways. The inverse square law is equally punishing if you move closer to a source.
Let's consider a scenario often analyzed in hazard planning. A worker is stationed 9 feet away from a source, taking a reading of 250 millirems per hour. To read a mechanical gauge, they need to approach the source, closing the distance to 4 feet.
Here, the hazard is condensing. The surface area of the sphere is shrinking rapidly. To calculate the new dose rate, we set up the ratio. The original dose rate multiplied by the old distance squared divided by the new distance squared.
So we take the old distance of 9 feet and square it, 81. We take the new distance of 4 feet and square it, 16. We divide 81 by 16, yielding a magnification factor of roughly 5.06.
We multiply the original 250 millirems by that 5.06 factor, and the new intensity is over 1,265 millirems per hour, or 1.26 rems per hour.
By walking 5 feet closer, the environment became 5 times more toxic.
It's a massive jump.
If a worker operates in that new 4-foot zone, they will completely exhaust their entire 5 rem annual legal limit in less than 4 hours. This mathematical reality is why industrial hygienists don't just rely on training. They paint physical, brightly colored concentric circles on the floor around sources. The math dictates the physical geography of the workplace.
Now, what if you don't have a meter reading to start with? What if you're sitting at a desk planning an operation, and all you know is that you have a 2 Curie source of a specific gamma emitter?
That's a very real problem.
The math gives us a phenomenal shortcut formula to estimate the dose rate at exactly 1 foot away, establishing the baseline you need for your inverse square calculations.
Let's share the shortcut.
The shortcut equation is S equals 0.5 times C times E. S is the expected dose rate in rems per hour at a distance of 1 foot. C is the activity of the source in Curies, and E is the energy of the specific gamma emission in MeV.
It is remarkably elegant. If you have a 2 Curie source and you know its gamma energy is 1 Me, you simply multiply 0.5 times 2 times 1.
And the result is 1.
That source will generate roughly 1 rem per hour at a distance of 1 foot. Once you have that 1 foot anchor point, you can apply the inverse square law to map out the radiation intensity for every single square inch of the room before a human being ever steps foot inside. It is pure hazard anticipation.
But inevitably, you encounter a situation where time and distance are not viable options.
Yeah, tight spaces.
Exactly. A worker must be stationed exactly 3 feet from a high-level source for a 12-hour shift to manually monitor a critical process. You cannot rotate them, and you cannot move them back. This forces us to pull the third lever of the safety triad. We must physically intervene in the path of the radiation. We must build a shield.
Which brings us to the science of attenuation. Shielding is not a one-size-fits-all proposition. It requires matching the physical properties of the shield material to the specific physics of the incoming particle.
Precisely. Let's revisit our particle breakdown.
Yeah.
Alpha particles, as we established, are massive, heavily charged bulldozers.
Right, the bowling balls.
They interact so rapidly that almost any physical barrier, a sheet of paper, a plastic face shield, even a few inches of dead air, will completely absorb them. Shielding alpha is trivial.
Gamma rays and X-rays, on the other hand, are highly penetrating, massless photons. They don't interact easily.
Not at all.
To force an interaction, you must place an immense amount of electron density in their path. You need heavy, high atomic number materials, lead, thick steel plates, or massive pores of high-density concrete. You are essentially building a dense forest of atoms to trap the photons.
And then we have beta particles, high-speed electrons. This is where shielding becomes a highly dangerous, counterintuitive engineering trap.
Let's explore this deeply because this is a classic failure point in safety engineering. Let's say I'm an inexperienced safety manager. I have a powerful beta-emitting source on a workbench. I know lead is the ultimate heavy-duty radiation shield for dangerous gamma rays. So naturally, I assume lead is the best possible shield for everything. I build a thick lead box and place the beta source inside. I assume I have solved the problem.
If you do that, you have not solved the problem. You have engineered an entirely new, potentially more lethal hazard. You have weaponized the shield itself.
Let's walk through the exact physical mechanism of why that happens. It's called Bremsstrahlung radiation, right?
Yes. Bremsstrahlung is a German term that literally translates to braking radiation. Remember that a beta particle is a lightweight electron traveling at an incredibly high velocity.
Like a sports car.
Lead is a massive, incredibly dense atom with a massive positive charge in its nucleus. When that speeding, negatively charged beta particle enters the dense, highly charged environment of a lead shield, it is subjected to immense electromagnetic forces.
It gets pulled and decelerated violently.
Exactly. It slams on the brakes. But the fundamental laws of thermodynamics dictate that energy cannot be destroyed.
The energy has to go somewhere.
Right. When a high-speed particle is violently decelerated, all of that forward kinetic energy has to go somewhere. The beta particle sheds that excess energy by emitting an X-ray photon.
So the lead successfully stops the beta particle, but in doing so, the violent deceleration physically generates a secondary cascade of highly penetrating X-rays. You've essentially built an unpowered X-ray machine.
You really have.
The worker who thought they were protected from beta radiation is now being heavily irradiated by secondary gamma-like photons blasting out of the lead shield.
Which is an absolute catastrophe. To safely shield beta radiation, you must use materials with a very low atomic number, typically an atomic number of 13 or lower. Aluminum, wood, or ideally thick plastics like plexiglass or lucite.
Why do low atomic number materials work?
Because their nuclei are much smaller and have much weaker positive charges. When the high-speed beta particle enters plexiglass, it isn't violently yanked to a halt.
It's a gentler stop.
Yeah, it decelerates gradually, bumping through the lighter electron clouds, losing its kinetic energy slowly in the form of mild, harmless heat rather than violent X-ray bursts. You are giving the particle a soft landing pad instead of a brick wall.
That physical distinction is paramount. But once we had selected the correct material, say lead for a gamma source, how do we mathematically determine exactly how thick that wall needs to be? We don't just guess and stack lead bricks until the meter drops. We calculate the half-value layer, or HVL.
The half-value layer is the shielding equivalent of the half-life. It is defined as the precise physical thickness of a specific material required to absorb and attenuate exactly 50% of the incoming radiation intensity.
Just as decay is an exponential curve in time, shielding is an exponential curve in physical depth. To calculate the half-value layer of any material, you take the natural logarithm of our familiar constant of 0.693 and divide it by a value called the linear attenuation coefficient, denoted by the Greek letter mu.
The linear attenuation coefficient, mu, is a physical constant that describes how efficiently a specific material absorbs a specific energy level of radiation. Every material has a unique mu. High-density lead has a very large mu for gamma rays, meaning it attenuates them rapidly over a short distance.
And air.
Air has a microscopic mu, meaning the gamma rays travel vast distances before being absorbed.
So if you have a gamma beam and the reference tables tell you the mu for aluminum against this specific energy is 0.2 inverse centimeters, you divide 0.693 by 0.2. The resulting half-value layer is roughly 3.47 centimeters.
What that mathematical result tells the safety engineer is that every time they add a 3.47 centimeter slab of aluminum to the wall, the radiation intensity passing through will be cut exactly in half.
So it scales down cleanly.
If you start with 100 rems, one layer drops it to 50. A second identical layer drops it to 25, a third to 12.5. It is an exponential decay of intensity across physical space.
Which leads directly into the master attenuation equation. If we want to know the exact intensity passing through an arbitrary thickness of shielding, not just neat half layers, we use the formula I equals I0 multiplied by E to the power of negative mu times X.
The architecture of this formula is identical to the radioactive decay formula we used earlier. I0 is the original unshielded intensity blasting against the inside of the wall. I is the final attenuated intensity emerging on the outside where the worker is standing.
And the exponent.
E is our exponential base. The exponent is the negative attenuation coefficient, mu, multiplied by X, which is simply the total physical thickness of the shield in centimeters.
Let's conceptualize the math. If you have a high-intensity gamma source, and you plug in a large mu because you are using lead and a large X because the wall is thick, the negative exponent becomes very large.
Right.
To a large negative power becomes a very tiny fraction. You multiply the original intensity by that tiny fraction, and you prove mathematically that the hazard has been neutralized to safe levels.
There is a slight complication when dealing with thick shields, represented mathematically by the buildup factor, denoted as beta. When you fire a dense beam of radiation into a thick wall, not all the photons are cleanly absorbed or pass through. Some hit atoms and scatter, bouncing around inside the shield like pinballs.
This scattering effect means that just inside the shield, or slightly behind it, the radiation can actually bunch up, creating a localized intensity that is slightly higher than a pure, perfect, exponential absorption curve would predict.
Exactly. The buildup factor corrects for this internal scattering. However, in the context of standard industrial hygiene calculations and compliance testing, OSHA and most regulatory bodies assume a buildup factor of 1 for general radiation workers, effectively neutralizing it in the equation for basic protection planning.
Good to know.
It is a vital concept for advanced nuclear engineering, but less critical for routine facility shielding calculations.
So we have mastered the physical threat, the labyrinth of units, the exponential clock of half-lives, and the geometry of time, distance, and shielding. But all of this relies on data.
It absolutely does.
How do we actually extract these measurements from the invisible environment? We can't manage what we can't measure.
The translation of invisible quantum mechanics into actionable safety data is achieved through specific instrumentation. And we divide these tools into two distinct operational strategies: personal monitoring and area surveys.
Let's delve into personal monitoring. This is about capturing the cumulative, individualized dose a specific human receives over their shift. The legacy workhorse here is the film badge.
The film badge is an elegant application of historical physics. The earliest discoveries of radioactivity by scientists like Henri Becquerel involved noticing that uranium salts spontaneously darkened enclosed photographic plates.
And the badge uses that.
A film badge uses that exact same mechanism. It contains a small piece of specialized photoemulsion film wrapped in light-proof paper, housed inside a plastic holder.
The plastic holder usually has different physical filters bore into it, a small window of aluminum, a tiny piece of copper, and an open window.
Yes, and those filters allow the lab to differentiate the type of radiation. High-energy gamma penetrates the copper. Beta might only penetrate the open window. As the ionizing radiation hits the film, it chemically alters the silver halide crystals in the emulsion, exposing the film just as visible light exposes camera film.
At the end of a month, the worker turns the badge in, the lab chemically develops it, and they measure the exact optical density, how black the film became. That darkness is mathematically correlated to a precise REM dose.
But there's a big downside.
Right. The drawback, of course, is the profound lack of immediacy. The worker receives their exposure data weeks after the physical interaction occurred.
To improve durability and precision, modern hygiene relies heavily on TLDs, thermoluminescent dosimeters. Instead of chemical film, TLDs use solid-state physics. They contain small crystalline chips, commonly lithium fluoride.
How does a crystal record radiation?
When ionizing radiation penetrates the lithium fluoride crystal, it transfers energy to the electrons within the crystal lattice. This energy excites the electrons, kicking them up into higher energy states.
Okay, they're excited.
But because of the unique structure of the crystal, these electrons become physically trapped in these high-energy traps. They are locked in place, storing the radiation's energy like a microscopic frozen battery.
And how do we extract that data? Thermoluminescence? Thermo meaning heat, luminescence meaning light.
Exactly. When the badge is sent to the lab, they place the crystal in a reader and apply precise heat. The thermal energy agitates the crystal structure, releasing the trapped electrons.
So they fall back down.
As the electrons fall back down to their stable resting state, they release that stored energy in the form of visible light photons. A photomultiplier tube measures that flash of light. The intensity of the flash is flawlessly proportional to the exact dose of ionizing radiation the crystal absorbed over the month.
It is brilliant solid-state memory. But both film and TLDs are historical records. If a worker is executing a high-risk entry into a valve room where dose rates are intensely high and their LRA time limit is 12 minutes, they cannot wait a month for a crystal to be heated.
No, they'd be in serious trouble.
They need real-time data.
For immediate, acute monitoring, workers utilize pocket ionization chambers. These resemble thick writing pens clipped to a lapel. Inside the pen is a miniature gas-filled chamber containing a central quartz fiber that has been given a static electrical charge.
And what does the charge do?
Because it's charged, the fiber physically repels away from the central post, bending outward.
And as the worker enters the radiation field, the incoming gamma rays ionize the gas inside the pen. Those newly created ions neutralize the static charge on the fiber.
Right.
As the charge dissipates, the fiber slowly relaxes and moves back toward its resting position. The worker can unclick the pen, hold it up to a light source, and look through a built-in magnifying lens. They see the shadow of the fiber moving across a physical scale, allowing them to read their accumulated dose instantly, moment by moment.
That covers the human body. But what about the environment itself? Before the worker ever enters the room, the industrial hygienist must map the ambient hazard. This requires area survey instruments.
And the most iconic tool in the arsenal is the Geiger-Müller tube, or GM counter. This is the device that creates the classic, terrifying clicking sound we associate with radiation.
The GM tube is a marvel of amplification. It consists of a metal cylinder filled with a low-pressure inert gas, like argon, with a high-voltage wire running down the absolute center. When a single particle of ionizing radiation enters the tube, it strips an electron off an argon atom.
One ion pair, that's a microscopic electrical signal. How does the machine read it?
The high voltage applied to the center wire exerts a massive pull on that freed electron. The electron accelerates violently toward the wire. As it accelerates, it gains so much kinetic energy that it smashes into other argon atoms, ionizing them as well.
It's a chain reaction.
Those new electrons accelerate, ionizing even more atoms. It creates a massive, cascading avalanche of electrons hitting the central wire simultaneously.
A microscopic physical event is amplified into a macroscopic electrical pulse. The meter registers that massive pulse as a single count, translating it into an audible click.
Because of this violent avalanche effect, GM tubes are incredibly sensitive. They can detect a single beta particle. This makes them unparalleled tools for qualitative analysis, finding a tiny speck of contamination on a workbench, sweeping a worker's boots for radioactive dust, or answering the binary question, is there radiation leaking from this pipe?
But their extreme sensitivity is also their analytical weakness.
It is.
Because every single particle triggers a massive identical avalanche, the GM tube cannot tell you what kind of radiation it just detected, nor can it differentiate the energy level. A weak beta particle and a powerful gamma ray both produce the exact same click.
Sure.
If you need precise quantitative measurement of specific particles, you must use more sophisticated tools.
That is when professionals deploy proportional counters, which operate at lower voltages to measure the exact amount of primary ionization without the full avalanche, allowing them to distinguish between alpha and beta particles. Or they utilize scintillation detectors, which rely on materials that emit microscopic flashes of fluorescence when struck by radiation, allowing for precise measurement of gamma energy spectrums.
All of this instrumentation, all of these exponential calculations, all of the deep physics, it all funnels into one ultimate objective: the industrial hygiene program. How do these numbers dictate reality on the plant floor?
They dictate every single action through the strict application of the hierarchy of controls. The survey instruments gather the raw N0 activity data. The industrial hygienist applies the inverse square law and attenuation mathematics to that data. If the calculated dose rate exceeds the ALARA targets, it triggers immediate engineering controls.
You don't just tell the worker to walk faster. You physically alter the environment. You install a 2-inch thick lead glass viewing window. You design custom, elongated robotic handling tongs to artificially impose distance between the hands and the source. You pour denser concrete.
If the hazard cannot be engineered away to acceptable levels, the mathematics then dictate the administrative controls. You use the linear time equation to calculate a maximum permissible exposure window of exactly 18 minutes.
Very strict windows.
You write standard operating procedures enforcing strict shift rotations. You implement physical lockout procedures for the high radiation zones based entirely on the calculated decay curves.
And finally, the personal dosimetry data drives the medical surveillance program. If a worker's TLD badge returns from the lab showing an unexpected anomaly, say, a localized dose of 3 rems over a single weekend, the occupational health physician doesn't guess at the biological impact.
No guessing allowed.
They know exactly what physiological systems to monitor. They order immediate blood work to count the lymphocytes, looking for the telltale biological indicators of an acute exposure event, tracking the unseen damage to the DNA. The physics dictate the engineering protects the biology, and the biology is continuously monitored to verify the physics. It is a unified, closed-loop system of human protection.
It is a profound responsibility. When you are performing these calculations, whether in a quiet office or under the pressure of an ASP exam, you are not doing abstract algebra. You're utilizing the fundamental laws of the universe to shield human life from an invisible, silent destroyer.
We have covered immense ground today. We started by conceptualizing the microscopic violence of ionization, stripping electrons from their orbits and threatening the very structure of DNA. We broke down the confusing sequence of units, tracking the radiation from its activity in Curies, its travel through the air in renins, its absorption in rads, and finally quantifying its biological destruction in REMS using the critical LET-based quality factors.
This is quite the journey.
We learned to wind the exponential clock of half-life, both forward and backward, predicting the future and reconstructing the past. We mathematically mapped the geometry of the expanding sphere to leverage the inverse square law, and we analyzed the physics of attenuation, avoiding the lethal trap of Bremsstrahlung by matching the shield material to the particle. Finally, we translated all of those calculations into physical reality through advanced detection instrumentation and rigorous program controls.
To the listeners absorbing this, the mathematics of radiation are dense, but they are logical. Once you understand the physical mechanism, the why behind the formula, the calculation becomes intuitive. You are acquiring the analytical vision required to see the invisible.
But before we conclude, we must acknowledge that the landscape of this profession is not static. Our understanding of the physics is complete, but our methods of measuring it are evolving rapidly.
Throughout our entire discussion today, our administrative and engineering controls have relied heavily on generalized mathematical averages and periodic delayed feedback loops. We calculate a room's dose rate, we assume a worker's position, and we assign a shift time. We check a TLD badge a month later to verify our assumptions.
It's safety based on historical averages and static geographic assumptions.
Exactly. But we are currently standing on the precipice of a revolution in digital dosimetry and spatial tracking. We are seeing the deployment of active, wearable sensors integrated with AI-driven, three-dimensional spatial mapping. These systems track a worker's physical location down to the millimeter in real time, overlaying it with live environmental sensor data.
So instead of calculating an assumed dose based on a static 4-foot distance and a 2-hour shift, the system measures the exact fluctuating dose rate the worker's chest receives, second by second, as they move dynamically through the hazard zone.
The implications for the ALARA philosophy are staggering. The provocative question we must face is this. As real-time, high-definition data becomes ubiquitous, how will our historical mathematical definitions of compliance shift?
That's a great question.
When we no longer have to rely on generalized mathematical averages, will the rigid, standardized shift rotations become obsolete? Will we move to a model of dynamic, micromanaged exposure limits tailored to the biological reality of the specific worker in the exact moment? Or, when the digital systems fail and the sensors go blind in a crisis, will these fundamental physics formulas, the hand-calculated decay curves and attenuation equations, forever remain the ultimate, undeniable bedrock of human safety?
It is a profound shift in how we manage risk, transitioning from predictive math to reactive real-time data. But until that future arrives everywhere, the math is your greatest asset. Thank you for dedicating your time to this intensive session of QHSE Talks. Whether you are facing the ASP version 11 exam or managing a complex industrial facility, I urge you to internalize these concepts. Master the exponential functions on your calculator, understand the geometric realities of the hazards, and remember that when you step into an environment where your human senses are completely blind, it is your mastery of these physics that shines a light in the darkness. Keep calculating, trust the math, and stay safe out there.